All right, so let's talk about the temperature. This temperature is also a weird feature that water has. Go back to kinetic energy. Kinetic energy is energy in motion, motion energy, not potential energy, but when you let go of that spring, as it coils back up, it releases energy, right? Kinetic energy. So it's energy in motion. Atoms and molecules are always moving in random fashion. Even in something like this ruler, they're still moving in there, but they're very, they're very close together moving. They're almost like vibrating. But in a liquid, they're doing like this, and in air, they're going like this. But even in a solid, it's still moving, and they're moving in random spots. The faster they move, the more kinetic energy they're producing. Now we have this thing called thermal energy, which is basically kinetic energy released from this molecular motion. So it is a type of kinetic energy. All right, we just call it thermal energy. Heat is the measure of the total amount of this total energy. That's what heat is. Okay? Which leads to temperature. Temperature measures the intensity due to the average thermal energy. Okay, so it's all about the thermal energy. If I go back again over here, heat is the measure of the total amount, whereas temperature is the measure of the average amount of thermal energy. Okay? You use these terms all the time, right? Heat and temperature, but now we're defining them in a scientific way. Okay? So an example, when you heat your coffee, the average thermal energy increases and the thermometer records this as a rise in temperature of the liquid. Right? That's what's happening with that. The total thermal energy also rises, meaning heat. So heat and temperature are not the same thing, right? Temperature is the average, whereas the heat is the total amount. So we have this Celsius scale that we deal with in real life, in science. In America, we use the Fahrenheit, right? So it measures temperature in the world, whereas Fahrenheit is really more common in America. So these are the two formulas. Again, if I'm asking on a test, I'm not going to ask you to use a calculator. I just want you to be able to come up with a formula for this, because there's going to be times you're going to need to convert. Okay? And that's what it is. So water, just to give you an idea, scale-wise, water freezes at 0 degrees Celsius for 1 in Fahrenheit. 32. Okay? And water boils at 100 degrees Celsius for 1 in Fahrenheit. 212. So look at the Fahrenheit scale. You got 32 to 212. You got Celsius, 0 to 100. So it's not really for every 2 points you go up or 2 degrees. There's got to be some sort of that, or I've also seen it with fractions and stuff. So just so you can see what that is. I don't know why, like the metric system, I don't know why America chooses not to do that. There's too much memory in America. 32 to 212, I'll deal with the 0 to 100. It makes more sense, right? So one of these days, America will join forces with everybody else. But in science, they're always using a metric system. They're always using Celsius. So you got to learn how to convert them, okay? All right, calories. You know what a calorie is. Those small little bugs that go into your closet and start sewing your clothes together. So when you put it on, you can't fit it into your clothes, right? Yeah. That's what a calorie is. No. A calorie is a unit of heat. Okay? So when you talk about heat, how much heat it produces, it's so many calories. Okay? So the amount of heat it takes to raise the temperature of 1 gram, see again science, 1 gram of water by 1 degree Celsius. Okay? Also, it is the amount of heat that 1 gram of water releases when it is cooled. So going back the other way, too. A kilocalorie is 1,000 calories. And this is what's on all your nutritional facts. All right? It's the amount of heat it takes to raise the temperature of 1 kilogram of water by 1 degree Celsius. So when they say, they're actually lying to you. All right? When you see that, you eat a bowl of cereal and you want to see the side over there, they tell you how many calories it is. It isn't calories, it's kilocalories. They fool you on that. Okay? So that's what it is. It's really kilocalories on that. Okay? A joule is not what you have on your ring, right? A joule is 0.239 calories. And you'll see that often too. 1 calorie is 4.84 calories. I won't ask you about these conversions over here, but when you read the book, they're going to be used in terms of kilocalories and joules. I just want to put it on here on a PowerPoint so to be complete, so you have a place to go to if you're confused with what the definitions are. But that leads to specific heat, the heat capacity. So specific heat is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree. I'll give you examples of what I mean by this. It's how well a substance resists the changing its temperature when it absorbs or releases heat. You have to put a lot of heat into something before you actually can touch it. See, water doesn't have that. Well, water has a lot, yeah, that water does have that. You have to put a lot of heat in it. A good example of this is, well, here, let me just do this. So specific heat of water, 1 calorie per gram per degree Celsius. This is a very high specific heat. There's not much in the world that actually has this high specific heat. The opposite, look at ethyl alcohol, which is really the alcohol that's in alcoholic drinks, okay, ethyl alcohol. So you only need 0.6 calories per gram per Celsius degree. That means you only need 0.6 calories needed to raise the temperature of 1 degree or 1 gram of ethanol. This gives you an example of, if you take a pot, an iron pot, and you fill it with water, you put it on the stove and let it sit there, all right? Let it sit there for a couple minutes and it's heating up, right? If you touch that handle, you're going to burn your hand. But if you put your finger in that water, it's only on for, I don't want you to do this, don't let it cook and boil, but if you put your finger in there, likely it's just going to be lukewarm. It's not going to be the same temperature as the iron handle, because it takes a lot more energy to heat up water than it is to heat up other things. Does that make sense? Do you see the significance of this? Okay? That's what's nice about this. Okay? They have other things that they could actually use, but they have to make it synthetic. Sure, you can put water in your car, and that'll cool it down, but the car gets really hot. So we have something called antifreeze that even has a much higher specific heat than water, and it doesn't really get that hot. Okay? So the significance of this water's high specific heat. It's in a heat bank. That's what water is. It can actually store a lot of heat, even though heat's going to it. When you put your finger in that water that was only on the pot for a couple minutes, it's just a little bit warm, if that. But you put a lot of heat to it because it holds the heat in, but it doesn't release the heat that's going to burn your finger. That's a very interesting thing that water does, that other things don't. So water tends to resist changes in its temperature. It takes a long amount of heat to really get it hot. All right? So water absorbs and holds a large amount of heat energy with only a slight increase in temperature. It eventually gets hot, sure, but it takes a long time, a long amount of heat to do that compared to other substances. So it allows you to, the water will absorb the heat from the air, right? It absorbs heat if air is too warm. So that cools down the air up, if it's too hot. It releases heat if the air is too cold. Okay? So this prevents rapid changes in our body temperature to sustain life. We're warm-blooded creatures. right? So we could do things. We could stay in the cold. We're not going to freeze so fast. We're going to do other things. I'll show you that too. Okay? So how can you explain why we have this fantastic property of water? What's going on here? Okay? It has a high specific heat. Again, it's these hydrogen bonds that you're going to see that's doing all this wonderful stuff. Okay? Hotter air. And I'll show you how the hydrogen bonds are going to be helping out with this specific heat. Hotter air. Heat absorbed is going to break the hydrogen bonds. Okay? You put enough heat in there, it's going to break the bonds. Most of the 1 calorie heat is used to break these bonds, not for making the water molecules move faster. So look what's happening here. You have these hydrogen bonds, and they're there. Heat is going to break them up. So the heat is going to break them up. So if we have, and I'm just giving you numbers, but let's say you have 100 units of heat going into this pot of water. Okay? Most of that heat is going to be used to break up the hydrogen bonds, not to heat up the water molecules. Does that make sense? Okay? Once they're all broken, then it's going to heat up the water molecules and then they're going to start evaporating. So that's why we have this weird specific high specific heat of water. So that's what happens in hotter air. Cooler air, heat release will form the hydrogen bonds. Okay? So when the temperature of water drops slightly, many additional hydrogen bonds will form and start making sludge and eventually ice, right? Right? So this releases a lot of energy as heat, and that's what happens. Okay? So what about the specific heat and what does it do to life in general on Earth? So we have the oceans that can absorb a lot of heat because of this mechanism, right? The ocean has all these hydrogen bonds with all the water, okay? So it absorbs the heat from the sun at daytime, and the oceans warm up very little, okay? Because that heat is going to be used to break up the bonds, not so much to heat up the water molecules. So it doesn't really change that much. Does that make sense? The temperature doesn't change in the water as much. Oceans can gradually release the heat to warm up the air at nighttime. So it gets cooler. The sunlight's not there. So now it's going to start making the hydrogen bonds come together, and it releases heat as it does that. So the oceans will cool down very little because it takes a lot of energy, or the energy that's inside the water is going to be used to make the bonds themselves, right? So the ocean's temperatures are stabilized to favor marine life, right? Fish are cold-blooded animals. They don't like the change in the water, otherwise they will freeze, kind of thing. You know, they hibernate and things like that. So this helps to keep the ocean's temperature pretty stable overall, all right? 71% of the Earth is covered with water. That's a weird fact. 71%. That means only 30% land, all right, or 29% land. So water keeps the temperature fluctuations on land and in water within limits that permit life. Okay? Organisms are made up of, MUO is made up of, okay, mainly water, and can better resist their own temperature changes by doing this kind of thing. So when you have something like this, all right, this is California, all right, so here's the Pacific Ocean and San Diego stuff. So what's happening here is that the high specific heat of water serves to keep the temperatures not really changing, okay, at the coastal areas. So you're seeing like 75, 84. That's about the same thing. When you're someplace very close over it, the water and the coastline is going to be similar because the heat is going to either go out of the ocean into the air or from the air and go back to the ocean. It's going to keep that area, the coastline, the same amount. But as you get further and further away from the coastline, the land isn't going to have the benefit of being close to the ocean. So it's going to get hotter. Does that make sense? Okay? So that's what's happening with that. Okay? Then we have something called evaporation cooling. Another weird phenomenon, all about the same thing here. Okay? Heat evaporation is the amount of heat that a liquid must absorb for 1 gram of it to be evaporated. How much heat do you have to put onto this water before it evaporates? So we have heat evaporation of water. And I'll give you examples again so you understand the situation. Well, we have a very high heat of evaporation. Not we, I mean the water molecules. To evaporate 1 gram of water at 25 degrees Celsius, about 580 calories of heat, a lot of heat, is needed to do that. You have to put a lot of heat to that for that to happen. To evaporate 1 gram of ethanol, right, the alcohol that's in alcoholic drinks, at 25 degrees Celsius, same thing, only half the heat is needed. It's going to take, it'll be easier to boil alcohol than it is to boil water, or be faster, because you don't need that much heat for alcohol. So a lot of heat is needed to change the water into vapor. That's the thing that's going on here. Okay? So the significance of this, of water's high heat of evaporation, is we have this water cycle that goes on. Okay? Sun's heat is absorbed by evaporating in tropical areas. All right? The vapor moves towards the Earth's poles and condenses to rain. So at the tropical areas, where that's, you go to Trinidad and those areas over there where the equator is, that's where it's going to be hotter, right? That's where the sun is going to be hitting most. So the sun's heat is absorbed by evaporating in tropical areas. So the areas that are going to be there where there's a lot of water, they'll evaporate faster than other areas, right? That are going to closer to the poles, because that's where the sunlight's hitting more. That's where the heat is more. So what will happen is, and I don't want to get into as a weatherman and stuff, but the way that the currents go, it goes from the equator and the currents go towards the poles. So it's going to take this vapor that just came from Trinidad and equator and those places over there, it's going to go into the vapor, go into the air, be carried with the currents, go closer to the poles, and since it's colder up by the poles, or closer like where we are, in Massachusetts, New Jersey and stuff, then it's colder in the air, so that vapor is going to condense and cause rain. Does that make sense? Okay? So you have that thing. So the rain goes down in rivers, goes back down to the equator, right? You got the Mississippi River that's going to go back down, and the whole cycle repeats itself and repeats itself. So you have this water cycle that goes on. Okay? Sweating. All right? Water in sweat absorbs excess body heat. All right? This cools us to evaporate things. Best way I can explain this is this. All right, you have water molecules. Oh, here, we've got our arm, right? Our arm kind of looks like this. Right? Hand, okay. And you're going to start sweating. You're hot, you're sweating. So how does this release heat? Right? You always hear, you want to sweat so that it releases heat. I see water. Okay. What's happening is air drops is, water, these sweat drops, you have this. Right? Let's have a lot of this going on. And you got these hydrogen bonds that are connecting these water molecules. And so, that right? And you got to think that it's all in that water drop, right? It's all doing that. So look what's happening here. You have bonds that are breaking and reforming, breaking and reforming. And this is what's happening. In the skin, you have molecules in it. Now, I'm not going to draw them all out, but let's say that's a molecule of your skin, that's a molecule of your skin, that's a molecule of your skin, that's a molecule, and so forth, right? This is your skin molecules. Well, they're moving, they're solid, but they're still like vibrating. When it vibrates, it releases kinetic energy. And that heats up your body. That's what's happening, okay? And in the heat, it's going to move faster, which means there's going to be a lot of energy coming off this. That's what makes you hot. But look what's going to happen. As this goes off, it's going to release energy as it's moving, and there's a water droplet on top of that. The energy from here, because in the heat, you're going to vibrate more. You don't see it, but the skin is going to vibrate more. This is going to release a lot of kinetic energy, which is going to go to the water droplet, and it's going to start breaking up these. The energy from your arm is going to start breaking up the hydrogen bonds over here. Now what's going to happen is you have a lot of hydrogen bonds with all your water molecules. They're going to break, they're going to reform, break, reform, break, reform. And the ones that are going to break, the ones that are closest to the top, they're going to break and they're going to evaporate. So what's going to happen here, as your body is getting hotter, it's going to transfer the heat from here, or I'm sorry, the energy from here into the water to break up these bonds and then change it into, and evaporates off your skin. So that's how it cools your body. You have to sweat to release that energy to cool your body. Does that make sense? All right. I'll have a little video, I saw it on Khan Academy, added to this lecture video that I'm doing here. And you'll see it on there, same thing. All right? But that's what it is. When you sweat, you're releasing energy. That's how they're doing. That's how you understand that. Does that make sense, everybody? Okay. The high humidity on a hot day. You increase the concentration of vapor in the air. There's so much vapor in the air because it's such... That's why I don't... Today's a nice day. It's like raining right now. All right? But you don't want to have something where it's hot, like 90 degrees. You get this little rain shower that's going to last for 10 minutes and it goes away. And then everything that's wet is going to turn immediately into vapor. So now you have a lot of vapor in the air. The humidity goes up. So now to produce this water coming out of your skin, but it's hard for it to evaporate because there's so much vapor that's out there. So that's because, so now this can't really, it has no place to go. It can't go out into the air because there's so much water molecules that are out there. So it stays in you and you feel clammy and just ugly within humid days. That's the reason why. Does it make sense? Right? Okay, because it has no place to go. So that's what makes us uncomfortable. All right, this high humidity. Okay? You go to Arizona, the humidity is very low. It doesn't rain there that much. It's hot as hell, but you don't have the humidity over there because it doesn't rain as much. So they're hot, but they're not so uncomfortable. Okay? So we have this evaporative cooling that happens, okay? Water molecules with the highest kinetic energy will evaporate first. Those are the ones that are going to be closest. If I do a sweat droplet, it's the one that's closest to the, furthest from your skin, closest to the air. Those are the ones that have the highest energy. Those are the ones that are going to evaporate first, not the ones closest to the skin. Okay? This releases energy leaving the water surface cooler, allows you to be a little bit cooler over there. Okay? The average kinetic energy, or temperature, will then drop. The best way I can explain what this is this. If you have 100 of the fastest runners at your school, and they transfer to another school, the 100 of fastest ones, that leaves you with runners still at the original school, but the average of the speed that you have left over there, doesn't that drop now? Because you transferred all your best ones. So you have the sprinters or the runners left at the original school, but they're not the best. So the average drops down. Does that make sense? So that's what's happening with this. The ones with the fastest or the best kinetic energy, that gets released first, which means the average of what your body temperature is going to drop, because the highest kinetic energy molecules left first. Is it clear about that? You see that? I have to do a lot of these analogies for this boring crap. Okay? I have to. And then that actually makes like a click with you guys. All right? And you can come up, that's what you have to do, is you have to come up with for yourself to understand it. You look at other books or different videos, or just come up with ideas of different examples than the ones over here. I could probably come up with hundreds of them, but I got to still move on with my lecture. But it's coming up with these different examples to help you understand what's going on. Okay?
So if you are like most of us, your body probably sweats when it is warm, when your environment is warm, and you probably realize that it sweats in order to cool itself, in order to keep the body from overheating. But you probably have wondered, well, how does this work? What is actually causing that? And the simple answer is it's happening, or what's allowing your body to cool, the chemical process, or I guess you could say the physical process is happening, is evaporative cooling. Evaporative cooling, which is really the notion that as that water, those beads of sweat vaporize, it's actually going to cool your arm down. But that begs the question, how does that actually happen? And so let's just visualize it a little bit. Let's just say that this is your arm. So this is your arm right over here. So let's say, I'm going to try my best, draw a quick arm right over here. So okay, that's your arm, and it's got beads of sweat. Let's say it's a hot environment. It's got beads of sweat right over here. And if we were to zoom in on that sweat, we would see the constituent water molecules. And sweat is mainly H2O. It is mainly water. Now, when we talk about the temperature of something, we're talking about the average kinetic energy. Each of the individual molecules, they all have different kinetic energies. They're all bouncing around in different ways and transferring the momentum in all different ways. And so you can imagine a reality. Maybe this one has a fairly high kinetic energy. It's moving in that direction. This one has a lower kinetic energy moving in this direction. Maybe this one has a medium kinetic energy moving in this direction. And maybe this one has a really high kinetic energy moving in that direction. And so we've already talked about how hydrogen bonds in water between the partially negative end and the partially positive ends, that's what keeps the water together. As these things move past and flow past each other, what gives the water its cohesion is these hydrogen bonds. But if all of a sudden, remember, we're talking about the average kinetic energy, but even if we're at room temperature and the average kinetic energy isn't so hot, you might have individual particles, individual molecules that actually have quite a high kinetic energy. And if they're in the right place, if they're near the surface and their kinetic energy is high enough to break the hydrogen bonds with neighboring water molecules and to overcome the pressure in the atmosphere. So let's say that these are just gas molecules in the atmosphere here, but it's enough to break free and none of these things bounce into it and force it back to form hydrogen bonds. This thing could actually break free and enter and become water vapor and become in its gaseous state. And it'll be so far apart from other water molecules that it won't form hydrogen bonds anymore. So by vaporizing, or by this process of evaporation, what's happening? Well, if your highest kinetic energy particles or some of your highest kinetic energy particles are able to escape, what's going to happen to the average kinetic energy? Well, as the highest kinetic energy things escape, and those are the ones that are most likely to escape, well, then your average kinetic energy is going to go down. So average kinetic energy is going to go down. Or another way of saying it is that your temperature is going to go down. Your temperature is going to go down because as these molecules turn into water vapor, they're going to be the highest kinetic energy of them. So energy is transferred to them and then they escape. And so what's left over is going to have a lower average kinetic energy. And you're saying, well, how does that actually cool down my hand? Well, your hand is made up of molecules as well. So let's say that this is the surface of your hand. Those are the molecules. They have some average kinetic energy. They are kind of vibrating in place, especially if we're talking about they're a solid. And so maybe I'll draw them more, they're vibrating like this. They're bonded to each other in some way. I won't go into the details of what types of molecules these are. But then if you have your water molecules here, water molecules that are sitting on the surface, and I'm drawing this as kind of a cross section. Let me draw the water molecules. I'll draw them as blue molecules. So this is an H2O right over here. H2O. This is an H2O. And this is an H2O. And they have some hydrogen bonding. So there's some hydrogen bonding going on. Well, as the high kinetic energy water molecules escape, say this one right over here escapes, and so the average kinetic energy of what's left over is lower. So then the temperature has gone down, and now your body molecules, the ones that are all warmed up because of whatever is going on inside of your body, well, those can now they can vibrate and bump into these water molecules and increase their kinetic energy more. Than the ones that have the most kinetic energy, those might escape again. And so one way of thinking about it is that all that heat is being used to allow these individual water molecules to escape in order to vaporize. And so that heat is leaving your body. So it allows you to cool down. Cooling down happens by heat actually leaving. So that's how evaporative, I wrote evaporative cool. That's how evaporative cooling actually works.